Binomial distribution. If every outcome of an experiment can be classified as either a success or a failure, and the probability of success is denoted by P, while the probability of failure is Q, where Q is equal to 1 minus P, then the experiment is said to be Bernoulli trial. The following are considered Bernoulli trials. A die is tossed once, and the number that will turn up is classified as odd, it's a success, or even, it's a failure. So if it's odd, it's a success. If it is even, it's a failure. Next example, a ball is drawn from a box that contains 5 red and 3 green balls. The outcome is considered a success if red ball is drawn. Otherwise, it is considered a failure. So as long as there are 2 outcomes, the first is the success and the other one is a failure. So we need to divide the outcomes into 2, the success and the failure. When an experiment is performed in a sequence of n independent and identical Bernoulli trials, then the experiment is called a binomial experiment. Thus, a binomial experiment possesses the following properties. The experiment consists of n repeated trials. Each trial is a Bernoulli trial. The trials are independent, and the probability P of success and the probability Q, which is equal to 1 minus P of failure, are constant for any or for each trial. If X is a random variable representing the number of successes out of these trials, then we say that the random variable X follows a binomial distribution, which is denoted by this symbol. A binomial distribution is a discrete probability distribution of the number of successes in a sequence of n independent experiments. When we say probability distribution, it is a mathematical function that gives the probabilities of occurrence of different possible outcomes for an experiment. The following are examples of binomial experiments rolling a pair of dice 6 times. So n is 6 here, and counting the number of times that an even sum turn up. If it is even, it's a success. If it is not, it's a failure. Tossing 3 coins 12 times, so n here is 12, and counting the number of times that more heads than tails turn up. So, more heads than tails is a success, otherwise, it's a failure. Taking random samples of size 10 from a shipment of batteries, which contains 5% defective units, and counting the number of defective units in the sample. So the defective units in the sample is the success. If it is not defective, it's a failure. A binomial experiment consists of n trials, with P as the probability of success and Q is equal to 1 minus P as the probability of failure. The probability that there will be K successes out of n is given by this formula. N taken K times P raised to K times 1 minus P raised to n minus K, where n taken K denotes the number of ways of choosing K objects from a set with n elements. So in other words, it's NCR. N take combination of n taken R at a time. So it's the same as this one. The above formula defines the probability mass function for the binomial distribution. So this one is the PMF of binomial distribution. The mean and the variance are NP for the mean, and then variance NP times 1 minus P. Example number 1. A machine that produces ball bearings is known to produce 5% defective items. A quality control technician takes a random sample of 15 ball bearings produced by this machine and rejects the production run if at least 2 of the ball bearings are found defective. Letter A, construct the probability mass function of the random variable x, which represents the number of defective units in the sample. Find the probability that the batch produced by the machine will be accepted. On the average, determine the defective items to be found in a sample size of 15 ball bearings. For letter A, since n is equal to 15 and the probability is 0.05 or 5%, using the definition of the probability mass function, for random variable, we have this one. 15, because that is n. Taken k, 0.05, that's the probability, 0.05, raised to k, and then 1 minus 0.05 is 0.95. Then 15 minus k, because 15 is n. For k, or if k is equal to 1, 2 up to 15. Again, if k is equal to 1, 2, up to 15. For B, the batch will be accepted if at most 1 defective unit is found in the sample, meaning to say less than 2. Because if it is at least 2 or 2 or more, the ball bearings found are to be defective or rejected. Hence, we have probability of x is less than or equal to 1. That is probability of 0 plus probability of 1. Plugging all the values, 0 for k, so 15, 0, or 15 taken 0, 0.05 raised to 0, 0.95 raised to 15, because 15 minus 0 is 15. Plus, let's have probability of 1, defective unit, 15 taken 1, 0.05 raised to 1, 0.95 raised to 15 minus 1. 15 minus 1 is 14. Simplifying this one is 0.95, 15, and simplifying that one is 15 times this. Adding all the values, we have 0.8290, meaning to say the probability of having accepted, the batch will be accepted. The probability of that the batch will be accepted is 0.8290. And the batch will only be accepted if at most 1 defective item is found in the sample of 15 ball bearings. Let's have letter C. On the long term, the average number of defective items that will be found in a sample of size 15 is, using this formula, mean is equal to n times p. Since n is 15 and p is 0.05, the mean is equal to 0.75. Meaning to say, there is 1 defective item for every sample of size 15. Since x takes only integer values, 0.75 is nearly equal to 1. So there is 1 defective item for every 15 ball bearings. Example number 2. An experiment consists of rolling a pair of dice and observing the number that turn up. Compute the following probabilities. A double. In other words, the two numbers that turn up are the same. Appears twice in 6 rolls. So a double appears twice in 6 rolls. The number that turn up are both even and occur at most once in 5 rolls. The sum of the numbers that turn up is at least 8 and occurs at least twice in 8 rolls. Let's have the first one. A double appears twice in 6 rolls. Let x be the random variable representing the number of doubles that turn up in rolling a pair of dice 6 times. There are 6 possible doubles. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So the random variable x is a binomial random variable with the probability of 1 over 6. Why 1 over 6? Because there are 6 over 36 combination. Again, there are 36 combination and there are 6 doubles. This one, and that one. And n is equal to 6 because we are going to do that 6 times. Rolling a pair of dice 6 times. So we have this probability of 2 because it says here appearing twice. So 6 taken 2 times the probability 1 over 6 raised to 2 times 1 minus 5 over 6. 1 minus 1 over 6 is 5 over 6 raised to 4 because 6 minus 2 is 4. Computing this, we have 0.201. So the probability of getting a double, which appears twice in 6 rolls, is 0.201. For letter B, let x be the random variable representing the number of times that the two numbers that turn up are both even. Since there are 9 pairs of numbers which are both even, like 2, 2, 2, 4, 2, 6, and so on and so forth, we have the probability 9 over 36, which is equal to 1/4. And n is equal to 5 because it should be 5 rolls. The required probability is, so according to the problem, at most once. At most once. So it should be probability of less than or equal to 1. So probability of 0 is this one. 5 taken 0 times 1/4 raised to 0 times 3/4. 3/4 because it's 1 minus 1/4 raised to 5. 5 is 5 minus 0. And then 5 taken 1 times 1/4 raised to 1 times 3/4 raised to 4. Computing all that, we have 0.6328. For letter C, let x be the random variable representing the number of times that the sum of the numbers that turn up is at least 8. There are 15 pairs of numbers whose sum is at least 8 from rolling the pair of dice. This gives us the probability 15 over 36, which is equal to 5 over 12. Like for example, at least 8, we have 4 plus 4, it's 8. And then 4 plus 5, it's 9. And n is equal to 8. Because it should be rolled 8 times. The desired probability is, according to the problem, occurs at least twice. At least twice. So it should be probability of x is greater than or equal to 2. probability of x greater than or equal to 2 is equal to 1 minus probability of x is less than 2, which is equal to 1 minus probability of 0 plus probability of 1. At least twice. So it should be getting probability of 0 plus the probability of 1, and then you subtract that to the entire 100% probability. That is how we get at least twice. So computing for that, we have 1 minus probability of 0 is 8 taken 0, 5 over 12 raised to 0, and then 7 over 12, because that's 1 minus 5 over 12 raised to 8. That's 8 minus 0. 8 taken 1 times 5 over 12 raised to 1 times 7 over 12 raised to 7, because it's 8 minus 1, 7. Compute this first. You subtract that from 1, and then you will get 0.91. The probability of having the sum of the numbers that turn out is at least 8, and it should be occurring at least twice in 8 rows is 0.91.